You know that? Yeah, they know it. But tonight he's going to entertain you by talking about science.
So yeah, never been done before in Central Arts, so I thought I'd try to come up with something really original. All I want to do is, Frank's going to project a photograph that I really like, a really good photo behind me, and I'm going to try and explain to you why I think it's so great. See. Can we put the lights on? So to kind of get this photo, you just need a sense of scale. So I'm going to start with something we think is pretty big, the biggest thing that we can touch, which is the Earth. So we think that the Earth is this big old ball of rock flying through space. But you take a small step back and look at the solar system. Actually, all of the solar system we're speaking about is the Sun, essentially, 99.8%. And most of the rest is Jupiter. Mercury, Venus, Earth, Mars, they're tiny specks of dust of no significance whatsoever unless you happen to be living in one of them. So the Sun is pretty big. In fact, the Sun is so big that the weight of all that stuff, the gravity generated by all that stuff, it squeezes it all together and you get small atoms, hydrogen atoms, fusing together into helium atoms. And that fusion generates heat and light, and that's why the Sun shines, and that's why we're all alive. But helium is as heavy as the Sun can get, and helium, as we know, is the stuff that makes party balloons go up. It's pretty light. If you want to make bigger atoms, carbon, or even iron, you're going to need a bigger star. So if you want to make iron, you need a star that's about 20 times the size of the Sun, 20 suns, all put together. And now you've got this enormous gravitational energy, all this stuff crushing into itself. And these stars, these giant stars, they burn really fast and really bright, and after about 1 million years, there's this big core of iron in the centre of them. All these smaller atoms are fused together. But gravity is still trying to squeeze the atoms closer and closer together. There's a problem, because once you try to fuse atoms into bigger than iron, instead of releasing energy, it absorbs energy. So the star runs out of fuel, essentially. And the next bit that I'm going to describe, what happens as this star dies, actually happens faster than I can explain it to you. It takes about 10 seconds for about what I'm going to tell you in the next minute or two to happen. So all the heat, the energy that was being created by fusion, suddenly is gone. Gravity is still there, so this star collapses under its own weight. It collapses, and you've got all this matter, 20 suns worth of matter, falling down, collapsing down towards the core of the star. And that kinetic energy of that generates an enormous heat, an almost unimaginable heat, 6,000 billion degrees, 6,000 times hotter than the core of the Sun. And at that kind of temperature, when matter gets to that kind of temperature, you get really strange shit going on inside the atoms. You get the production of antimatter. Antimatter is what it sounds like. It's like normal matter that we're made of, but it's the opposite. When it meets normal matter and interacts with it, both are annihilated, and the energy that's wrapped up in matter is released. Now, to give you an idea of how powerful that is, 1 gram of matter contains about the same amount of energy as was released in the bombs that were detonated over Hiroshima and Nagasaki. 1 gram. If my antimatter doppelganger appeared here and we touched and annihilated each other, well, some people might be happy about that, but they wouldn't be around for very long to enjoy it, because instead of Ireland, there'd be a big hole at the bottom of the Atlantic Ocean. Inside this star, 2 suns worth of matter is converted into energy, and you get the biggest explosion in the universe. You get this enormous explosion, so great that this single star shines for days or weeks afterwards. This single star shines brighter than all the other stars in the galaxy combined. So what it looks like from Earth is, you've got a dim speck of light in the sky. It's actually a distant galaxy of hundreds of billions of stars. And suddenly it brightens 5 or 10 times. And that's where the name for this event comes from. It's a supernova. And this bright, extraordinarily bright new star appears in the sky. Now inside this supernova, there's all this matter flying around. Atoms are being ripped apart, atoms are being fused together. And the only place where any element, any atom that's heavier than iron, so gold is one that we all know about. All the gold, if you've got gold jewellery, all the gold in the universe is made in the death throes of this dying star, the maelstrom of energy and fusion that happens inside there. And that's what this photo is. It's what a supernova looks like about 5,000 years later. You can see you've got a ring of expanding gas still on fire, a nice sphere, and eventually that sphere will expand out until eventually the inexorable pull of galaxy will make it collapse on itself, and new stars and new solar systems will be formed. And maybe in those new solar systems there'll be a few specks of dust left where carbon-based life forms can evolve to the point where they're able to dig the gold out from under the ground at their feet and wear it on whatever appendages are culturally appropriate. And at the very centre then of this cataclysm, this explosion, the components of atoms, neutrons, are crushed and crushed and crushed together to a sphere of unimaginable density, a sphere about 20 kilometres across, with the weight of 2 suns, 700,000 Earths crushed into a sphere 20 kilometres across. And in this case behind me, because of a slight asymmetry in the force in the direction of the explosion, that neutron star is called, that sphere, has been propelled outwards. And you can see this tongue of flame, this filament of fire leading out, that's penetrated through the expanding cloud of gas and dust. And if you look at the very end of that, there's a tiny point of light, and at the centre of that tiny point of light is this neutron star, travelling at 1,000, not 1,000 kilometres per hour, travelling at 1,000 kilometres per second, which is fast enough to eventually escape the gravitational pull of the galaxy itself. It'll travel through interstellar space to who knows what end. And I can't help wondering if someone somewhere with a very different perspective of time and space to ours is saying, good shot. Thanks very much.